go back and review a few old things about velocity, acceleration, and force from last week, and the interactive you guys had yesterday to work on kind of hit on all those. But a couple important things: keep using my object on a string in a circle. Let me make my screen biggest right now for you guys at home. So just using this as our example, an object just going around on a string. At any given moment, if we asked if it was released, how it would fly off, how did we say? You remember, Dom? Straight line, straight off the path of where it's traveling. The specific word for that was tangent to the path, okay? Which basically meant that. So that's because at any given moment, the velocity vector points in that direction. When we used that ladybug thing from last week and we drew these in, and also yesterday, it should have hit on that again by drawing the vectors on. Then we got into the acceleration. We said anything that is moving in a circle has a centripetal acceleration. The word centripetal meant towards the center, and it was an acceleration not due to speeding up or slowing down, but due to changing direction, and it pointed inward. Then after going over some things with that, late last week, we brought in the force aspect. If something's accelerating, a force has to cause it. And we generally called forces that cause circular motion, we put them in a category called centripetal forces. And then one of our last assignments last week was to identify specific forces that were centripetal. So if I'm swinging something on a rope to make it go in a circle, the centripetal force was due to what? Tension, exactly. If it was something like this, like going through a roller coaster loop or a track loop, it was normal force. Oh, I didn't make it go fast enough. If it was a car going around a turn, it was friction. If the turn was banked, it was friction and normal force, because that was one of our questions. So it could be a combination of some of them as well. And another common one that makes things go in circles or turns is gravity, especially for like orbits and stuff like that. Now that was mentioned on one of our last study guides, but after we go through circular motion, we're going to go on a little unit of like orbit stuff all by itself, because it's a little unique, but it does tie in with this stuff. All right, so that brings us to our last concept lesson on this stuff today. So we told you that when we're swinging something like this, that the force is inward from the string pulling on it, the tension, because it's centripetal, and so is acceleration. So the next question is, I didn't tell you anything wrong there, but if the force is to the middle and the acceleration is to the middle, the next question is, why when I swing this thing, doesn't it, as it goes around the circular path, why doesn't it go towards the middle? We're telling you there's a force towards the middle. We're telling you there's acceleration towards the middle. But this thing clearly is not moving towards the middle, right? So the question is, what makes it stay on the outside of the path? Something's going to make it, because the only force present is pointing this way. But why doesn't it actually move that way? Any ideas? Any thoughts? Something we... Okay. Okay, you're on the right track. Well, I'm just going to slightly reword what you said. Okay, but you're pretty much on. So instead of using weight, I'm going to use the term mass. They are almost the same thing, but mass doesn't care about gravity. All right. So once we put this mass in motion, there was a term we learned about sometime before Christmas break, with just forces in general, called inertia. All right. Inertia, things that have more mass have inertia. So you're exactly on the right track there. And just where we want to be real careful, we don't want to say it forces it out. It does seem that way. It definitely does seem that way. But the only force is towards the middle, the tension. But what happens is the inertia of the mass in motion wants it to fly off. We just can't say it's forcing it off, because the only force, again, is towards the middle. But it wants it to fly off. Inertia is not a force, it's a property of mass. And when you put something in with mass into motion, the faster it goes, really you're creating it a situation where it wants to fly off more and more. If you ever swung anything on a rope just messing around like this, you could even tell the faster you swing it, you could feel the tension increase as you spin it faster and faster. That's because it wants to fly off more and more, right? Than when it's going slow. It wants to fly off the path when it's going slow. and the tension's not letting it, right? The string's pulling it back, not letting it. Keep it. Then that interaction of that centripetal force and the fact that its inertia wants it to fly off is what makes it stay on the outer part of the path. And the faster I pull it, I feel more tension on my hand. The faster I spin it, because this tension has to increase. The faster it goes, the more it wants to fly off, even more than when it was just going slowly like this. And if the tension can't hold up, theoretically, I can't, but like maybe a machine can, spin this thing so fast that maybe it spins so fast that the string can't hold it on anymore, right? If it spins way, way crazy fast, more than I'm doing it, then the tension could actually break possibly, and then it would go flying off in a straight line, and apparently the door's open still, out into the hallway. The main point is inertia is what makes it want to fly to the outside. And we could give some other examples of this that we probably felt before. If you are in a car and go around a turn, especially a sharp turn kind of quickly, you could feel that your body wants to shift to the outside of the turn. So if let's all pretend we're in the driver's seat of a car going around a right-hand turn right now, okay? So we're in the driver's seat, and if we turn right, our bodies might sway into the door, okay? It would sway to the outer part of the outside of the turn. If we were going a left-hand turn, our body would sway towards the middle of the car because that's the outside of the turn. And the faster you're going and the sharper the turn, the more you might feel that. If you've swayed so far to the outside of the turn, you might even press into the door some. Then the door presses back in on you to not let you fly out, right? So there's going to be some situational questions that go along with that. If we take that idea and put it into like a motorcycle, if you go around a turn sharply on a motorcycle, you want to lean into the turn. You know, if you ever watch like real fast, like motorcycle racing, they lean into the turn because it's on two wheels. That's to counteract the fact that it wants to push. You want to fly off your inertia. If you try it on a motorcycle to go, or a bicycle even, riding a bike straight up without leaning in a turn, going around it pretty fast, you'll probably tip the other way, and that's not good, right? It's all about effects of inertia. So what keeps you on the outside of the circle is inertia. You want to, the object wants to fly off at any moment, but something's not letting it. The tension in the string, maybe it's the normal force in a roller coaster loop, something like this. All those things we identified. So that's the main idea behind the next study guide. So for those of you at home, this is a pretty quick one. So I'm going to give about 10 to 15 minutes tops for everybody to work on it right now. All right, and before the end of this class period, I'm going to go over the answers to it. So Dom, you could find it and do it right now. But like always, just do your best on it. Don't spend forever on it. Answer the questions thinking about what we just talked about and with the review things we discussed. And we'll go over all the specific answers. Quiz tomorrow. You guys could use all these study guides from today and pass the 3 from last week on the quiz tomorrow. Okay, going over this one, there's a few review questions to start. That reviews inertia and really where it came from, since that's what we were talking about. So, old Newton's first law from a while ago. First review question. An object at rest will remain at rest, and an object in motion will remain in motion with the same speed and direction unless acted upon by an unbalanced force. And inertia is a natural tendency of an object to resist change in its state of motion. Main thing is inertia is not a force. But we have a situation like I was describing a little while ago about, imagine you were in a vehicle turning, right? So what all this big ugly paragraph tells us is that these two dots on the car, on the original car here, the dot with an X in it is the driver, the dot with the blue dot's the passenger. All right, so what this car is going to do, it's going to approach a turn and just slightly begin to start turning at about point A. So it asks us to do some stuff with this dot. And it also says, imagine we're in a vehicle that you're on a bench seat in a vehicle, and it says that it's made of vinyl so you slide very easily. Okay? So that way, if you were in this car, unbuckled, hopefully you wouldn't be, but unbuckled and you could slide very easily, what would your body do? Okay, so we already deemed it would go, your body would sway, or in this case slide, to what part of the turn, the inside or the outside? As you're going, you want to fly off the outside of the turn, right? So one thing it asks us to do, okay, first is just describe the motion of the passenger from the start until the turn at point B. Point B is when we really start getting into the turn. And actually, question 3 told us to put point B on there. Point A was here. So we were going pretty straight up to point A, right? Where it was very noticeable that it was turning. Now, this is up to judgment. So if you put point B like right after point A, that's fine with me, okay? On the key, they have point B right here. But I would say anywhere after point A, it's noticeable that it's starting to turn, right? So I don't be too picky with that. So it describes the motion of the passenger from point B to the rest of the turn, through the rest of the turn. So the passenger, if they were free to slide, as we go through the turn, should like be closer and get closer and closer to the driver until they're like right up against the driver, right? And the driver, you could see, gets closer and closer to the door, which is like the dotted line here. The driver would slide into the door, the passenger would slide into the driver. So as long as you kind of drew those dots close together to the outside part of the turn, that's how you would slide. You'd want to fly off. The door wouldn't let both of you. The door wouldn't let the driver, and you'd slide into the driver. And then it says, describe the motion of the passenger from point B to the rest of the turn. So from point B on, the passenger curves because the car is making them. But up to point A, they're going in a straight line because the car hasn't turned yet. Number 5, from point B for the remainder of the turn, place arrows on the diagram indicating the direction of the force the driver is pushing on the passenger with. So the passenger is flying into the driver, but the driver's body is actually putting an inward force back on them to go through the turn. So the force is inward. Just like I said, when we swing something like this thing in a circle, the force is inward, right? It's not outward. The effects of inertia are outward, but they're not a force. The only force is still inward. Even though you're sliding, you eventually press into the door or the person next to you, and they push back on you with a centripetal force making you go in the circle. So that's why all the force arrows should look something like that, pointing towards, we can't see the exact center of the circle because this is a partial turn, but they should look kind of like they're pointing towards the center of the turn. And number 6, in this example, the collision between the passenger and the driver could be explained by, best answer is C. A and B are out because they both say outward force, and we already said there is no outward force, right? So just due to that reason, C has to be right. The passenger traveled straight ahead, and an inward force pushed the driver into the passenger. There's no outward force. When we're done with these study guides, I'm going to spend another moment talking about that, because early on, when this stuff was first studied by scientists hundreds of years ago, that was kind of debated because it sure feels like there's a force on you, right? If you're a person in a vehicle, it feels like there's an outward force, but it actually isn't. You feel a force inward, and the effects of inertia is outward, not a true force. All right, moving along, there's a couple questions, 4 questions on the other side. All right, kind of a big situation here described for a small answer, but it said Rex and Doris are making a rapid right-hand turn in a vehicle. So this is like the situation we just went over. Doris begins sliding across the vinyl seat and collides with Rex. To break the awkwardness of the situation, Rex and Doris begin discussing the physics of the motion that was just experienced. Rex suggests that objects that move in a circle experience an outward force. All right, so hopefully we already realize that's not true. Doris disagrees, arguing that objects that move in a circle experience an inward force. In this case, according to Doris, Rex traveled in a circle due to the force of his door pushing on him inward. Doris did not travel in a circle since there was no force pushing her inward. She merely continued in a straight line until she collided with Rex, and that's basically what we drew on the last page. Who is correct? And from all that, Doris has to. It says argue one of these two positions. You don't have to write a book like I did here. Honestly, the thing that gives it away the most is that there's not an outward force in circular motion, so Rex has to be wrong because he said outward force. All right? You want to just keep going in a straight line. It's just that something's not letting you, okay? Whatever's making you go in a circle isn't letting you go in that straight line, and that's why you feel force to the outside even though there's not a true force. Number 8. No formula guides a golf ball around the outside rim of a green at a putt-putt golf course. When the ball leaves the rim, which path would it follow? So this actually goes back to some old stuff. If it, like, rimmed out, basically, as they'd say, right? It would follow best path 2, because that's the one we described and reviewed earlier. That's tangent to the path in a straight line, right? So 2 is explained why you could just say that. You could say anything wants to fly off in a straight line, specifically tangent to the path. Any explanation like that would be fine. Moving along, number 9. Suppose that you are the driver or passenger in a car and you travel over the top of a small hill on a road at a high speed. As you reach the crest of the hill, you feel your body still moving upward. Your glutes might even be pulled off the car seat. It might even feel like there's an upward push on your body. The upward sensation is best explained by which of the following? Don't pick any that's a force, so that again narrows it down. B, C, and D are all wrong because they all say, or B is wrong because it says an upward force. All right, but it's explain this upward sensation. Remember, you want to go to the outside of turn. So a hill is like a turn, right? It's just a vertical turn when you're riding on the top of it, right? So when that happens, we've all probably experienced this before on a road. If you ever went over like a quick bump on the road, you might get that like stomach dropping feeling for a moment. Or on a faster roller coaster where you go over the hill, a bump. You really feel that, right? The reason why you feel like that is because as you approach the top of the turn, at every moment you want to fly off of it. So in a vehicle not going too fast, you shouldn't actually fly off of it, but your body is not 100% locked into the vehicle even with a seatbelt on. You're free to move a little bit, right? And your body might continue to go up for a moment at the peak of that turn. So what causes a sensation is choice A, the tendency of your body to follow its original path. You know, especially like I said on a roller coaster, you come up to that top of a hill very quickly. You feel this to the extreme. It is true that there's a centripetal force in your body, but that centripetal force is not what's making you want to fly off and have that upward type feeling. So C isn't right. There's a word in D called centrifugal, which I have not mentioned yet. So hopefully you didn't select that one, because that's actually we're going to see as a false force. All right, final one. Number 10. This is describes what used to be a pretty typical ride at a lot of amusement parks, but not too many of them exist anymore. But there's a little diagram of it. Darren's on a barrel ride at an amusement park. He enters the barrel. It's just like a cylinder, basically. Okay, Kennywood used to have one of these, but they took it out quite a long time ago. But some of them still exist at some other places. The ride operator flips a switch and the barrel begins to spin at a high rate. The operator flips another switch and the platform underneath the feet of this person down here drops out and Darren's plastered to the wall. Now, there's another ride that you might know of that doesn't quite do this, but it's similar. If you've lived around here for a while, you probably went to Idlewild. You've been to Idlewild? All right. Remember the ride called the Roundup? All right. It's not exactly what they're talking about here, but it's similar. It lifts you up almost vertically after it goes fast enough, right? So you're in a cylinder, though, right? Because there's a wall behind you, a big cylinder. But obviously doesn't lift you up immediately. It has to get you going fast enough. And the faster you go, it feels like you're more pressed against that wall, all right? But that's because of inertia. You want to fly off. Not that it would happen, but if that thing started spinning real fast, like it does, and the wall behind you would disappear, you'd be in trouble, wouldn't you? You'd fly right off, right? The wall pushes back on you, and because you want to fly off, it feels like you're forced outward, but you're actually not. There's not a force. You do want to fly offward, but the effect of the force is inward on you. This wall is pushing towards the center of the circle on you. But that interaction makes you feel pressed to the wall. Okay? If you were ever on that ride and lean forward, it feels like it sucks you back, right? Because your inertia wants you to fly off. But then a rod like the one at Idlewild like that, it starts lifting somewhat vertical. You want to fly off so much that you're basically stuck to that wall. And then it's safe to lift it up as long as you're going fast. All right? It wouldn't be safe if you're going slow because you wouldn't want to fly off that much, right? My thing I always laugh at about that ride is that little chain they put there. Like as if that would do anything if something went wrong, right? But this ride's similar that they're talking about here. But these types of barrel rides, they don't lift up. They spin you real fast, and then the floor drops out from under you, and while you're spinning, you stay sucked to the wall, basically. And friction interacts. There's normal force, but if you remember from a few weeks ago, normal force is one of the two factors that helps make up friction. So because there's a real high normal force on you because you want to fly off so much, there's a great amount of friction on you, so you could stay up with no floor under you. You could relate that to the Roundup ride at Idlewild. A lot of people you see on that ride, they pick their feet up off the ground and put it on the wall, and they don't slide down, right? And you'd be fine just like that. So this ride basically drops that out, and you still stay up. All right, so anyways, this sticking to the wall phenomenon is explained by the fact, and the best answer is B. Darren has a natural tendency to move tangent to the circle because of his inertia, but the wall pushes him inward. That's the best answer. A is wrong because it says it pushes outward. It does not push outward. You feel like you want to fly off outward, but it's not a push, because a push would be like a force. It has nothing to do with air pressure. C has something about that. And choice D, I hope nobody picked that because it doesn't have anything to do with cotton candy either. All right, so main point of all these questions, to sum it all up, the reason why you stay on the outside of the circle is because of inertia. The only force is inward, not outward. But one last thing, since we have a few minutes left here, I put, like always, the links in this assignment to the Parts on Physics classroom that discuss this as well. And there was 2 links that actually went along with this study guide. One of them was a link that said the forbidden F word. And it's referring to a falsely named force that sometimes still gets used today. Remember, the only force is centripetal, inward, right? We already learned that word. Centripetal means inward. However, a long time ago, there was some scientists disagreed and said, well, this is a force that's forcing you outward, which we later deemed was just really the effects of inertia. But it was given a name back then called the centrifugal force. So if you look closely, the true force that's inward is spelled like this, centripetal. But this false outside force was once named the centrifugal force. And it, hundreds of years ago, got deemed that is not a true force. Okay, there is no true outside force, but somewhere along through history, this term still gets used. We just need to understand that it's not a true force. Anytime somebody might try to tell you there's such thing as a centrifugal force, it's actually the effects of inertia like we just talked about. But that term even got put into other things like the term centrifuge, if you ever heard of a centrifuge before. Usually the term centrifuge is what we use to describe the separating of particles or even fluids in some cases by spinning them in a centrifuge. A washing machine, a typical washing machine, could be described as a centrifuge. And what happens on the spin cycle of a washing machine is it spins them all inside. The washing machine's a cylinder, essentially. It might as well be like a cylinder on the ride we were just describing. It doesn't let the clothes fly out, right? Because they're stuck in that cylinder. But there's a bunch of little holes in the cylinder. And those holes allow water to fly off, right? And because the water wants to go to the outside too. And essentially it separates, not all, but a lot of the water away from the clothes in a process that's sometimes referred to as a centrifuge. Where that name comes from is from this false force that was no longer recognized to be true. But that term still gets used. If a washing machine didn't use a spin cycle, your clothes would be like sopping wet when you take them out. And they would take forever to dry, even in a dryer. So just the engineering of a simple washing machine takes into consideration this idea. You know, it wasn't like somebody like guessed into that. The first washing machine that was made like that, it was kind of, for such a simple thing, a pretty brilliant idea. Get them partially dry by just putting a bunch of holes in this tub and spin it real fast. It uses this same idea. So main point is centrifugal is not really a force, even though some places still falsely refer to it as one. Centripetal is. That's towards the center. All right. So that's pretty much the end of all the basics with circular motion. Have your study guides. There's 4 total. There's one on speed and velocity, one on acceleration, one on force, and this one on inertia. If you have those in front of you while you take the quiz, all of you will be at home tomorrow. Just get it in by the end of the day. It's all multiple choice. There is going to be one small mathematical problem on it. On the very first study guide, we did some problems on it. The equations on it, speed and velocity. We figured out how to find the speed around the circle. Formulas on that very first study guide. There'll be one very similar to like we did on that one there. So if you have them, you just kind of follow what we did, and it shouldn't be too difficult. You could use a calculator on your Chromebook if necessary.